Hi and welcome everyone to part 7 of the supplementary coding along video series for the Build a Large Language Model from Scratch book. My name is Sebastian Roschka. I'm the author of this book, and in this video I want to teach you how to teach LLMs to follow instructions. It's essentially one of my favorite topics. You, of course, probably are familiar with ChatGPT, where we can ask ChatGPT simple questions like translate maybe hello world to German and other simple things or even complicated things, and the LLM will assist us with that. And so we are building in this chapter a small personal assistant that can do similar tasks. And in my opinion, that's one of the most fun things one can do with LLMs. So in the grand scheme of things, where we are here in the final section of this book. So previously we coded the LLM architecture, set everything up to pre-train the model, and then we loaded the pre-trained weights from OpenAI. And using those weights in the previous section, we fine-tuned the model as a classifier, which was fun. And so the model was able to say whether a text message was spam or not, but it was also pretty limited. It could only say spam or not spam. So in this chapter, we will be making the model a bit more general, that it can that the model can respond with free-form text, and it can also process multiple types of queries. So it's more able to understand what we want from the LLM, and it is more flexible and can do more things. Of course, the model we are going to develop here won't be as powerful as something like ChatGPT, because that would cost us millions of dollars, and we want to keep it a bit simpler for educational purposes so that you don't have to spend millions of dollars. But the concepts are similar. So here we are just doing it for a smaller model with a smaller data set and so forth. And yeah, I think it's a lot of fun, and it also helps us understand essentially how these technologies or how these techniques work that we use to develop these technologies. So for that, like I start every notebook, I will first show you the software libraries, the Python libraries I'm using. So here, there are no big surprises. Everything here is the same that we used for chapter 6. And by the way, just going back here, this chapter is independent of chapter 6. So you can see here in stage 2, we had the pre-trained model, and then we loaded the pre-trained weights. And then there's this fork here where we either fine-tune the model as a classifier or as a personal assistant. But it's there, you can see there is no arrow going from here to here. So it's totally disconnected to chapter 6. It's just that some of the ideas in chapter 6, like the fine-tuning, that of course also applies to personal assistants, where we start with a pre-trained model. But similar to chapter 6, we will start with a pre-trained model. But yeah, if you have watched chapter 6, these libraries are the same, because we still need briefly TensorFlow for loading the OpenAI weights, but then all the other libraries here, matplotlib for visualizing the loss function, TickToken for tokenizing our inputs, Torch as our main deep learning library. This is still the same, so everything else should be similar to what we have used before. And then let me show you also the different steps we will be going through. So it is going to be, I would say, a relatively long chapter, but I think also many of these concepts are quite familiar. So in chapter 6, for example, we spent a lot of time setting up the data set. Again, we have to set up a data set. It will be a different data set, but many of the ideas also still apply. So even though it might look a bit like it's a long chapter, a lot of this will be quite familiar because we already spent so much time working on these things. Yeah, after preparing the dataset, we will be loading the open weights from OpenAI, similar to what we have done in chapter 6. And then the fun part will be instruction fine-tuning the LLM. And then I will also show you how we evaluate the LLM. Because yeah, if we have free-form answers, like this, it will be a bit trickier to evaluate how good the answer is, because in previous chapters we could just compute in chapter 6 the accuracy. We can see 50 out of 100 predictions are correct, so we can say it's 100%, 50% accuracy. Now it's hard to say because it's more free form. It's hard to say what is correct or not, especially if we have trickier answers where there can be multiple correct solutions. So if I say, what is the synonym for happy, there might be multiple synonyms. It has no one correct answer, for example. So it will be a bit more challenging to evaluate the LLM, but we will get to that in due time. First, we have to, of course, fine-tune the LLM. And for fine-tuning the LLM, we do need to set up the dataset. So should have added the section title. So the section title here is preparing the dataset for supervised instruction fine-tuning. So the dataset, I will just put it here because the code is not super interesting. So what we are doing here is we are downloading a dataset that I prepared. So I just call it instruction data JSON. And this is on GitHub, in my GitHub repository here. And here I'm essentially just downloading the file. So the file has 1,100 training examples. So it's relatively small, and this is mainly to keep the time that it takes to train the model relatively short. So I think it takes about, again, 5-10 minutes to train the model. Of course, the more the merrier. So typically LLMs, they are instruction fine-tuned with, I would say nowadays, at least 100,000 training examples. But again, this would be more expensive. So for educational purposes, this is a simpler data set I developed here. And we can take a look at some of the entries to get a sense of how it looks like. So JSON is essentially, yeah, it's a text file, but it looks like a Python dictionary. And so you can see each entry. So here I'm just taking the entry at position 50. Is a Python dictionary now. And so it has 3 input fields. It has an instruction field where it's, yeah, including the instruction, identify the correct spelling of the following word, for example. And then the input field contains the word that yeah, corresponds to this instruction. And the output field contains the answer that we want the LLM to generate. Maybe let's take a look at another one here. So here we have one where we have an instruction, but we don't have an input. So the input is empty. So we could also have a format like that. So for example, I could also technically, if you look at the, oops, sorry, yeah, here we go. So if I look at this format, and I can also convert it into a format where we don't have an input field. For example, I can maybe restructure it like this, and then it will be also a similar format. So it's not super strict. The reason also why I structured it like that is, and like here, it's the classic format. It's called the alpaca format. So, but you don't have to strictly use that format. I think in the appendix section here in the references and further reading materials, I also suggested some other data sets that are available on the internet, and not all the data sets follow this instruction. Honestly, it doesn't really matter. We can make it whatever we want. We can define our own format and our own style, because we will be also defining our conversion style, everything, so in a few moments. So I would say, yeah, don't get too stuck on how this is formatted. This is just one way of formatting the input. Let me maybe go back here and show you a figure. So the input is in JSON format, for example, like I mentioned. And then next, what we are going to do is, because we are not feeding the LLM in data in this format, we are feeding the LLM plain text. So we are going to convert this dictionary structure into, yeah, human-like text, how a human would provide the instruction. So here, this is one way we can apply a so-called prompt style template. So a prompt style template takes this dictionary and converts it into text. And this is the alpaca prompt style template. Alpaca is one of the first, I would say, publicly available resources that did something like that. So it's kind of like a classic, and here I'm using the classic just because, you know, it's the foundation or the original that most people are familiar with, or it's just like, you know, one of them, one popular one. Of course, there are also other styles, but focusing for the alpaca on the alpaca prompt style for now, it works as follows. That we take an entry here, and then we prepend something. So we prepend this boilerplate that says below is an instruction that describes a task. Write a response that appropriately completes the request. And then we have an instruction field. So it takes this line here, adds some markdown syntax sugar to it, and then we have the input field and the response field. And again, this is just one way of preparing this. There are many other styles. Actually, each LLM nowadays has its own style. If you think about other LLMs like Meta AI's Llama models, Google's Gemma models, or Microsoft's Phi models. For instance, here I actually have an example of the Microsoft Phi 3 style. So here they used something simpler, where instead of having the boilerplate, they don't do any boilerplate. They just have the instruction directly here. There's also no input field. They merge the instruction and the input into one, and that is like users designating the user input, and then this is what the LLM should respond under an assistant field. So that is another way of formatting the input. Actually, I like this because it's shorter, and shorter is cheaper. So because if you think back of how the model generates text, the model is generating one token at a time. And so if you have twice as many tokens, it will be requiring twice as many iterations. So it will be more expensive to run the LLM. And so the shorter, usually the better. But yeah, we are using the classic here because I think it's good for educational purposes to, use something that is quite popular, and this could be a reader exercise. In fact, if you read the book, there are a lot of exercises throughout the chapters, and I will leave you to this exercise to, try out different style templates and see how it affects the performance. But yeah, so this is what we are going to code now. So we are going to convert this into what we have just looked at, this prompt style. So let me show you the function. This is a very simple function, format input, where we have the instruction text, and we have here the boilerplate that I just showed you. And then here we insert the instruction, this part, the content here. And then if we have an input field, we will provide the input. So we will create this if we have an input, and otherwise we will just leave it empty. And so this will be giving us the instruction plus the text. So let me call this on our example buff, the one we have here. Of course, I need parentheses. I don't know what I was thinking. Okay, so here, this is how the LLM will see the input. You can see we have these new line characters. So this is how the LLM would see it. For us humans, of course, it's a bit easier to read if we actually render these new line characters. So let me add a print here. So this is how the LLM would see it. And then we also need a response. So for example, we can write a desired response. So let's also maybe check out the other one here. So this would be that one. So we can see here there is no input field because the input is empty. So that worked. And then, yeah, we can also add the desired response. So the desired response is only provided, of course, during training, during inference. When we use the LLM, there won't be a response. So because the LLM is supposed to generate it. So here, but for the preparing of the training data, we will include the response. And by the way, I wanted to mention one more thing, maybe if that's confusing, because when we use this here, the ChatGPT interface, we didn't provide anything like that. So we didn't, we didn't input it like this, right? So we could have done this, but we don't write it like this, right? Because it would be really tedious if we as a human write the style out every time. And so in fact, LLM providers, they do this already in a sense internally, so behind the curtain. So it's similar to what we're doing here when we only provide an input and then we have a function that takes care of the formatting. Similarly, other services, they also do this behind the scenes. So we as a user, when we will get to that later, when we write the instruction, there will be something that will be prepared in the background, but we don't want to bother users typing this. So this is why you don't see it, why something like this works, and why we don't need this whole thing here. But anyways, getting back to the topic, so how we would prepare the training data. So this would be the data for pre-training the model. And then lastly, in this section, let me also prepare the training, test, and validation splits. So we will be using 85% of the data. So we have 1,100 entries. We'll use 85% for training, 10% for testing, and then the remaining 5% for validation. And so let's just briefly look at how large these sets are. So we have 935 training data points, 55 validation data points, and 110 test data points. And so in the next section, this will be a bit, I would say, it will be very important. In the next section, I will show you how we prepare this in terms of the batches. We will define the dataset class, and then also later we will talk about preparing the data loaders that we can then use during the fine-tuning. Yeah, so now after loading the data set, the next logical step is to prepare the training set batches that we will use in the data loader when we are training the LLM. So here is just a brief overview again, where we have all the 9 steps in this section. We are at step 2, and then later we will load these batches into the data loaders. It looks like it's a small step in the grand scheme of things, but it is, I would say, the most crucial aspect when instruction fine-tuning an LLM, because everything down here, like loading the pre-trained LLM, instruction fine-tuning the LLM, we get to reuse functions from chapter 5, because the instruction fine-tuning is still training the LLM to predict the next token in the data set. So here it's really important that we set up the data set correctly so that the model can actually learn like we want it to learn. And so it looks like a small section, but there are quite a few steps involved. Like I mentioned, one of the most crucial sections here. So we have 5 steps that we will implement in the data set setup. So we have step 1, formatting the data. So essentially applying this format function that we developed to convert the JSON entries into this text. Then we will use the tick token tokenizer to turn the text into token IDs. Then we will be padding the data set to the longest sequence. We will apply this here on a batch basis. In chapter 6, we padded it based on the longest example in the data set. We will be a bit more efficient here, and we will pad only to the longest element in each batch, because it's a bit excessive if we would batch it or pad it to the longest example in the training set. We will have a excessive amount of padding tokens, and to avoid that, we will apply the padding on an individual batch basis. For example, this could mean that one batch has the longest example consisting of 80 tokens, one could have 1,000 tokens, like another batch could have 500 tokens, and so forth. But we will get to this when we implement this. So the idea here, or the step is, we have the input token IDs, and then we are padding them to the longest element in the batch. And input token IDs here means this whole input text. So I realize it might be confusing because it contains the response here, but it's similar to chapter 5, where we are interested in training the LLM on the next token. Later, when we get to use the LLM on new data, this will only include the boilerplate here and the instruction and input. It will not include the response. The response is only necessary, of course, during training, because that's what we want the model to learn. So in this context, input IDs means everything up here. And so we have the input IDs here. And the next step would be creating the target token IDs for training. So the target token IDs are the input token IDs shifted by 1 position. Again, similar to chapter 5. So if our input token IDs are 318, 281, 12,064, our target token IDs are 318, 281, 12,064. You can see these 3 are here basically. So we are shifting it by 1 position. That means we are removing this first token here. And to make the input IDs and the target IDs the same length, we add an additional padding token ID. This is why you only see 3 here, 3 padding tokens, and here are 4, because yeah, we have to, if we remove 1 token here at the front, we have to add 1 more token to have the same length again. And yeah, but the concept here is the same as in chapter 5, that it is shifted by 1 position. A new concept here compared to, let's say, chapter 6, when we do padding, is that we, at the end here in step 5, we are replacing this excessive padding amount by mask tokens. Here, minus 100. And this will help us to ignore padding tokens during training. So padding tokens are used to make everything the same size so that we can create these nice tensors for training. But we don't want the model really to learn based on how many padding tokens we have. Because imagine we have an example. If it ends up in a batch where the longest example is 1000 and our example is 100, we have 900 padding tokens. And then it might influence the loss function. And compared to a different batch where there are only fewer padding tokens. So we don't really want to make our loss or anything dependent on how much padding we have. So by replacing these by these so-called mask tokens, we can ignore those in the loss. So the loss will not, let's say, consider those when creating when computing the cross entropy loss. But we will get to that later in the section. So here I just wanted to briefly outline the steps that we are going to take. So formatting the prompt template, tokenizing, then adding padding tokens, creating the target IDs, and then masking the excessive padding tokens at the end. By the way, we will keep one padding token here because we want our model to generate a response with a definitive ending. So pre-trained models, they always keep on generating more text if we let them. Here, we want the model to generate an end of text token, this padding token, 50,256, if the model is finished with the response. And so this will also allow us to be more efficient so that the model, that we don't have to iterate a max number of tokens, and then we know exactly when the model is finished. So one padding token is always kept. But we will get to that when we look at the code here. So let's start with the instruction data set that we will set up. So one more figure I wanted to show you. So here we have these 5 steps, 1 to 5, and we will be first coding steps 2.1 and 2.2. So these first steps, where the first steps include applying the prompt formatting template and then converting them to token IDs. So essentially going from this JSON format entry into the text and then creating the token IDs. So let's code this up. So for that, we will create an instruction data set. And this instruction data set uses the dataset class. It inherits from the dataset class, similar to what we have done in chapter 2 and chapter 6. And here, we just assign the dataset. The dataset here is the JSON dataset. We have a list. The list will keep collecting our token IDs for each entry. So if we have 1,000 training entries, this will be a list of 1,000 token ID lists. And so what we are doing is we are applying our familiar format input function. That is the function we used before on the entry that we iterate over. So that will create this format here in the center. So we are going from entry to this formatted entry. Next, we will also add the response text. So this is the response that we add to the input. And then we will encode this. So the encoding here means that we go from text into token IDs. Okay, so this is what we are doing. We are collecting them in the encoded texts. And then here, the length function will give us the length of the data set. Whether we call length on data or encoded text, it doesn't matter. It just gives us the length, which the data loader requires for the shuffling and so forth. And here the get item will return one item from our encoded text at a time. And so this is something that is used by the data loader to build the batches, similar to chapter 5 and 6. So this is our instruction data set here. Oops. And so this one will be based on the tick token tokenizer. So let me just, so that I don't forget this later, let me just import this. Oops. Tick token. And then we will have tokenizer.get encoding GPT-2. Sorry, I made a mistake. This should be, tokenizer equals tick token get encoding. Okay, so this is our tokenizer, and that is going to be used here. Now we have completed steps 2.1 and 2.2. And next we will create a collate function. So what is the collate function? First, this is just a draft. I call it draft 1 because we are going to refine it. But this is a function that will operate on each batch that the data loader generates. So later we will have the data loader like before when we create our, let's say, train loader. And the data loader will accept the training data set, which will be based on our instruction data set. And in addition, we will also provide a collate function. So here we would, for example, provide this one. And this will do certain operations on each batch, because right now we only implemented steps 1 and 2. Next, we want to take care of steps 2, 3, 2, 4, and 2, 5. And like I mentioned, we only want to apply the padding on a batch basis so that each batch is independent of the other batches, so that we don't have this excessive amount of padding tokens and so forth. And so the collate function will take care of steps 2.3, 2.4, and 2.5. Our first draft here, draft version 1, this is a very simple one. This will only do the padding here. So this will only do step 2.3. I will modify it shortly to also do step 2.4 and 2.5, but stay tuned for that. Let's do one thing at a time. So in that case, we won't technically use it like this. We will use a different collate function later. So let me just also comment this out so it's not too confusing. So how does the collate function work, this particular one? So here it receives a batch. This batch is created by the data loader, by the way, so we'll get to the data loader later. We will work with the collate function here in isolation, and we'll also test it in isolation, and later we will test it again with the data loader. But conceptually, this receives an input batch. We define what token ID we want for the padding, and then what device the data is supposed to be on. And here we determine the longest item in the batch. This is similar to what we have done in chapter 6. In chapter 6, we did that for the whole data set. Here we do it for each item only in the batch. We have an input list here, and the list will collect our padded inputs. So here encoded text collected our tokenized inputs. This is similar, but now we will have these padded inputs. So before we had just the regular token IDs. Now we will have the padded token IDs that we will collect here. And yeah, maybe you can pause and look through this. There might be different ways you can implement this. This is my way how I implemented this essentially. So maybe before I explain all the details why the +1 and the -1. So this is just one way I found that worked, because I did some experiments and I had sometimes an extra padding token or was missing a padding token. And with this implementation, I made sure that I always have the right amount of padding, where the padding is also determined here essentially by the difference between the longest element in the batch and then the actual length of that item, similar to what we have done in chapter 6. So when we add the padding token IDs, and then we keep adding the padding token IDs to our input list. So, and then at the end, we stack those. So because these are just lists, but the data loader expects batches, right? So the data loader passes a batch to this one that is in a tensor format, and it also expects as output a tensor. So here we are stacking those lists as a tensor. We are essentially just converting them into a tensor and then also putting them on the target device that we can choose, CPU, GPU, for example. But yeah, so maybe a lot of code here. If it's confusing, let us just test this in isolation. I mentioned in the next sections, we will be plugging this into the data loader, but it's not a bad idea to test this before we get to the next stage. So I hope also, by the way, it's not too loud in terms of background noise. There's really a big thunderstorm outside, so hope I don't lose power. We'll see. So here we are testing now this collate function in isolation on some inputs. So we have an input consisting of 5 tokens, 2 tokens, and 3 tokens. And ideally, what we want this to do is we want this to, so by the way, let's also just assemble this as a batch here. We want to assemble this in a way that we have the correct amount of padding for each of these items. And this will be determined by the longest element here. So ideally, we want to see that this will have 3 padding tokens. So they're not X, they will be token ID 50,256. And by the way, if you're wondering what these token IDs here mean, I just made up some numbers from 0 to 9, just so that it is a bit visually easier to read. Of course, these would be, in reality, when we apply it to our data loader, these would be the actual token IDs of the input, right? So I'm just having some sample here to play around with. And then what we can do is we can call this on our batch, and hopefully it generates the correct tensor. And we can see, yeah, so everything has the same length. Now we have padded the other ones so that everything has the same length. So that is essentially what our first draft of the collate function is doing. The next step will be creating the target IDs here. So for that, I could technically just copy this, maybe call that draft 2, and then I create maybe targets list here. Let me see what else. Yeah, here down here we will be also including the targets, and the targets are shifted by 1 position. So if I do targets torch tensor, oops, padded, and then there should be a parenthesis, of course. And then we are truncating. Oh, so we are essentially removing the first item from the input, which will mean that we are shifting everything over by 1 token. And then we keep collecting them in our list, targets. And then I think here we should probably also return those. Might be a good idea, right? Otherwise we do all the work and it is for nothing. Just double checking. I wrote targets as a plural, making sure everything looks okay. Okay, so there we go. So yeah, we mentioned returning, so let's not forget this. So now we have our draft 2. Let's see if that works. So shouldn't be append here. There we go. So now we have our, I mean, it's a bit hard to read. So we have the input and the target. So let's maybe also call or make 2 variables, and then it might be easier to read. So let's just do this. Let's look at the inputs first. So the inputs are the same inputs that we had before, ideally, because we didn't really change anything. We just added the targets, right? And so the targets are now shifted by 1 position. So instead of 0, 1, 2, you can see it's 1, 2, 3. So yeah, so that's it. So we have now created the target list. And the next step will be finally the masking, and that should be our last step in the collate function that we need. So then let's just call that custom collate here. And yeah, there are a few new parts I'm going to add. So first, what we need is, let's say, the ignore index. So for the ignore index, I'm using -100 because that's the default value that the cross entropy loss will ignore. Or we could use a different number and we can then change it in the cross entropy loss if we wanted to. So you can choose 99 or -1, but you just have to then make sure you update also the cross entropy loss. Personally, I just find it easier and more intuitive to just use the -100, which is the default ignored value in the cross entropy loss. And then let's also add a allowed max length to truncate in case we have inputs that are exceeding the context length that our model supports. So first, let me add the code for modifying the targets for with a mask token. So here, what I'm doing is I'm replacing all the target padding tokens by the -100, except one of them. We keep one of them because we want to teach the model when to stop generating text. So this one will be used to teach the model, okay, this is the stopping point. So then in the generate function that we have, we can check if end of sequence token is 50,256, or so if the current token we are generating is the end of sequence token, which is 50,256, then stop generating. And that is why we want to have it in here. The other ones we can ignore, like I mentioned. So here, that's what we are doing. So we create this mask. We check if a given token ID is a padding token ID. And then for each but the first one, we insert this -100 here. And that is one thing we do. The other thing I mentioned is we are also truncating to make sure that none of the tokens have more, so none of the training examples have more tokens than our context length of the LLM supports. So here we are just truncating by the longest sequence. This is really similar to what we have done before. And I hope this works. So I hope I didn't make a mistake. So if this works, let's just use this example again and see what we get. So we call it now custom collate. Call it on the batch, and then let's look at the inputs tensor. Looks exactly still like it looked like before, which is desired, right? We didn't change the inputs, but the targets, they should now contain our -100. So we can see everything but the first padding token got replaced with a -100, and that one will get ignored in the cross entropy loss. So before I end this video, let me briefly show you what I mean by that, because maybe you are a bit confused by that. What is happening? Why -100? What is this magic number? So I have a simple example here. So this is just so that we don't have to run the model, which we haven't loaded yet. I just have two training examples. So one example, just 2 token IDs, another example, 2 token IDs, and sorry, these are the one token ID with, so it's basically just a simple training example. Don't even think about it in terms of token IDs. Just think of it as the logits that the model outputs for the first training example. It could be similar to chapter 6, where this is the logit vector corresponding to the last token ID. I just want to illustrate something in the cross entropy loss here. So we have labels. Think of it similar to chapter 6. We have labels 0 and 1, for example, and then we compute a certain value here. What the value is, it doesn't really matter. What I wanted to show you now is if I add a new entry here, so just copy pasted that. If I add a new entry, let me do it like this. A third entry, and let's do -0.6 and 1.7 or something like, well, 1.6, I just typed it. It doesn't really matter, and let's give it also we need the target, right? Let's name this 2 so it's not overwriting our first example. And so what we'll get is a different number. Makes sense because we have added a new training example. When we compute the loss, it will probably be different from this loss. We have now 3 training examples. And I wanted to show you now the -100 illustration here. So let's increment this again so we're not overwriting this. So what will happen if I now replace this by -100? So if I replace this with -100, you will see this value is exactly like this value, because now the -100 tells the cross entropy loss, ignore this one. So that's just like a little trick that we can use to ignore certain token IDs. And here we apply this trick to ignore these excessive amounts of padding so that the model training is not influenced by these excessive amounts of padding tokens. So it's as if we didn't have any padding tokens. Padding tokens are still there because we need to make sure everything has the same length, but they won't influence the training. And so with that, we now have, we have explained how we batch the data. In the next section, we will talk about preparing the data loader. So yeah, in the previous section, we did already most of the hard work. That means implementing this custom collate function. In this section, we are now using the instruction dataset, the PyTorch dataset that we created earlier, and this custom collate function, put them together, and then we have a way to load the training and validation data for the actual fine-tuning. So we will begin with defining the device that we will be using. So everything in this notebook from now on will also work on a GPU if you have one, for example, a CUDA GPU. You can also replace this with MPS if you have Mac, which supports Apple Silicon. Now, I think still, based on my last experiments, you get slightly different numbers if you use the MPS device. So MPS is the GPU in the Apple Silicon chips. So it's basically on your own. I wouldn't say risk, but if you are open to get slightly different results, you might want to experiment with MPS, which will be faster than CPU if you're using a Mac. So here I will be running it on the CPU though, so that the values shown here should be similar to what you're getting on a GPU or a different type of CPU. And then one thing I wanted to also do first is defining defining a custom collate function, or a customized one. So we defined the custom collate function before, and remember there were a few settings we had. For example, padding token ID, we don't need to change that. The ignore index, we don't need to change, but we maybe want to change the device and the allowed max length. And so this is just like a Python basic. You just use func tools to make use the partial here to make a customized version of that. So that means it's just like a Python basic. That means if I use this one now, so if I call this one as a function, it will have the default values for the allowed max length of 1024, and it will use the device we define here. So that is all we are doing. It's really just like a Python basic. If you don't want to do it like that, you can also just go up here and modify those values here. Up to you. So, but that's usually how I prefer pre-filling function arguments with partial. So that's what we're doing here. And then we are ready to use the data loader. So here, that's just the PyTorch data loader that we used in chapters 5 and 6. We will again use 0 workers for maximum compatibility. We use a batch size of 8, the random seed for the shuffling. And so here I'm creating the training data set by passing the train data that we just generated earlier in this chapter to the instruction dataset class that we defined above, together with the tokenizer. And this then goes into the data loader. And so everything you are seeing here, all these settings except one, are the same that we used in chapters 5 and 6. So I'm not explaining again what drop last means, and also what the batch size means. You should be, I guess, already be familiar with that. What's new though is the custom collate here. So here we plug in our customized version, which uses max length of 1024, and then also the device, in this case, the CPU. So yeah, so that's what I'm doing here. I'm setting it up. For some reason, it's complaining. So let me go up here. Maybe I made a typo or did not execute it. Yeah, I did not execute this cell. So this is the instruction data set from the previous section. Now it should work. Yep, so there we go. So this is our training loader. And we can do the same thing for the validation and the test set. So here, the same thing. The only difference is that we don't need to shuffle and we don't need to drop the last entry here. So, but otherwise, similar to what we have done in chapter 6, same code as for the training set. Okay, and it's not a bad idea to take a look at like the results, that what the data loader outputs, just to make sure everything looks okay. So like usually I just tend to iterate over the data set, doing the iteration just to make sure everything looks okay. Remember now that each batch has its own longest entry. So one batch might have size 61, so 61 tokens as the longest entry. Some batches have 76, 73, and so forth. And yeah, that doesn't matter, because what we are doing is we are training the model to predict the next token. So we are not like in chapter 6, fixated on a certain token position. We are really more general. We have a free-form answer, and it can have different lengths. And it doesn't really matter how many padding tokens we have also, because we have this -100 here to ignore excessive padding in our loss function. However, we still have to make sure that each entry in the batch itself has the same length. Otherwise, we can't create a tensor, right? So that's yeah, looking good here. So we can see about yeah, most of the example have about like 70, 80 tokens. So it's a very small data set, 1,100 entries, and each example is also very short. I did that by design also to speed up the training. Yeah, in addition to that, also maybe not a bad idea to take a look at one of these entries to see that they look okay. So we can see this is the first yeah, training example. So here we see that, so this, if I iterate through this, inputs will default to the last inputs targets in the training order. So we are looking at the first example of the last batch. So I said, yeah, the first example in the last batch. So we are looking at the first row in this one. And so let me just do the length here. I can also do shape, but yeah, you can see that's the 69. Yeah, and we have the padding tokens as we would expect. Let's also check the targets corresponding to this one. So we can see here it's shifted by one position, right? So this is here. So that's looking good. And for the padding tokens, we still have that one padding token that we want to keep. So the model learns when to stop generating text via our generate function, text generate function. And then here the other ones, we have -100 because we don't want to have them influencing the loss during training because they're really just placeholders. Yeah, and this is our data loader now. It works, looks good. And in the next section, we will put it to action. Or maybe not in the next section, but in a few sections, because we still have to load the model itself, and then we can fine tune this. So the hardest work in this chapter is now done. We prepared the data set. Now the next step is, yeah, loading the pre-trained LLM that we want to fine tune in the upcoming sections. So for that, this will be actually pretty simple because we will be using almost the same procedure that we used in chapter 6. So that means we are loading the pre-trained weights from OpenAI. And for that, I'm using the download and load GPT-2 function from the GPT download file. So this is just something I copy pasted in here. This is the same one we used in chapters 5 and 6. You just have to make sure if you're importing it like this, that the file gpt-download.py exists next to this notebook where you're running this notebook. And then also from the previous chapters, we are importing the GPT model class and then the load weights into GPT function. And these are exactly the same things we used in chapters 5 and 6. The only new part, so everything you're seeing here is the same as we used in chapters 5 and 6. The only new part is that we are using a slightly bigger model now. So in chapters 5 and 6, we worked with 124 million parameters. Now we are working with a slightly larger version. And that is because I tried out the small version and it didn't do great. So when I trained it, the responses were really not good. And I thought, okay, I can't even tell that I trained this model. So I went one model size up and the results looked slightly better. So we could also go with these larger models. But the problem then is it's going to be slower. I'm running this on a MacBook Air computer. So, there's only so much you can do with a small old computer. So I think 355 is a nice sweet spot where we don't necessarily need a GPU to run this. Of course, ideally, I would run this on a GPU, and I actually did. But I wanted to make this code accessible to everyone or to most people. So I wanted to have an example that works also on on older hardware. And so yeah, this is a nice trade-off. I actually just ran this code cell before I was recording this section so that it doesn't take too long. It takes about I would say 4 minutes to download. It's 1.4 gigabytes. And yeah, so I have the files already ready. And this is essentially equivalent to what we have done in chapter 6, except now we have the larger model. And then next, I wanted to just double check how the model performs before we are training it. So here, just showing, I should probably import torch. So here, I think I see what happened. So what happened is because I mentioned before, I downloaded all the code, I restarted the notebook. Sorry, I meant I downloaded the model, and I must have accidentally restarted the notebook. So let's try this again. So we are just looking at some example text here. And so that's the input and then the instruction. And then let's use some of the things we have defined in chapter 5, the generate method, the text to token ID and token ID to text utilities. And so the text generated was the one where we applied the temperature scaling and the top K sampling. So it's just like that function we had to generate new text. And so this receives the model. We have our utility that converts text to token IDs using the tokenizer. We create 35 new tokens. And in reality, we could actually set this number larger if we have a fine-tuned model, because remember how we set up our data set. It will be generating or the model will hopefully learn to generate end of text token, right? So via the targets. So ideally a well-trained model will generate this token, and then with how we set up this generate function, it will stop generating text once it encounters this end of sequence token. However, our model is not trained yet, so it might not emit this end of sequence token. So we will just limit it to 35 so it doesn't keep on generating a lot of text, so that it is a bit faster here. So here we are just generating text, and then let's see how it looks like. You can see it takes a bit longer. It's a larger model now, and I'm just running it on a CPU. So yeah, so it might be here we are. So let's just maybe add a print statement here, so it's nicer. And you can see, it puts a response under response, which is kind of good. But then we can also see, that doesn't do anything. So we have an instruction, write a response that appropriately completes the request. The request is convert the active sentence to passive. The chef cooks the meal every day. So a passive voice would be the meal is cooked by the chef every day or something like that. Or we can see the model doesn't really do that. It's just repeating this, right? So and then it keeps just repeating. So in that case, this model is not very useful. I wanted to show you how it looks like before it's fine-tuned. And so our goal is to make sure that the response looks okay. And by the way we set up our generate function is it's also printing the input, which we don't have to show to the user, right? So if we use something like ChatGPT, it doesn't show us the input again. It just gives us the response, right? So in that same way, we can also set up our function that it strips off everything after the response. So yeah, what we're doing here is we are replacing this. So what we're doing is first we truncate this. So if we have our input text here, right? So the input text has length. Let's see, length input text. Length 200. So in the response, in the generated text, we are first truncating this off. Yep, there we go. So let me also print this. So we are stripping off the input because we don't need this, right? So ChatGPT also doesn't repeat the input. It would be very distracting. So here we have now the cleaned response. And then still, we don't need really this tag here. This is kind of like boilerplate. It's just a formatting style. So we can actually replace this by an empty string, and then also strip all the unnecessary new line characters. So if we prepare our output like this, it's much cleaner. So this is how the model would respond. And we can see the model doesn't really give the correct response. So fine-tuning the model will be hopefully making sure it gives us a better response. But yeah, I wanted to highlight that something like this is done also behind the curtains when we are using something like ChatGPT, where it also only gives us the response without any formatting boilerplate or any input repeated in the output and so forth. And so this is usually done by LLM apps in the background. Okay, so we are now set up. We have our model, which doesn't do perform well. So we want to make it perform well. And that is the topic of the next section, where we are going to fine tune this model. So now we are ready to take advantage of all the hard work we have done so far in this chapter when we prepared the data set, because now we can use all the functions we have defined in chapter 5 to instruction fine-tune the data on the data set we have just prepared. So when I started writing this book, I put a lot of thought into designing these functions so that we can reuse them, because that will make it more readable and I hope also more easy to follow. However, also in reality, it happens to be like that instruction fine-tuning uses exactly the same loss that we used during pre-training, namely predicting the next word in the text. The only difference now is, of course, that the text is slightly different structured from compared to pre-training. In pre-training, it was just raw text. Now we have these response and instruction fields and so forth. So, but the loss function is exactly the same, which is nice. So when we look at our previous chapters code file here, when we go to chapter 5, we can reuse certain aspects. I mean, we already reused the generate function just in the previous section. We can also reuse the train model simple function because it's exactly the same loss function. And then inside there, of course, we also have the calc loss batch and calc loss loader utilities. When you're running this, please make sure you're using the code from chapter 5 for the loss loader and not the code from chapter 6, because the calc loss loader in chapter 6 was using a calc loss batch version that was based on the last token. And here we're interested in all the tokens, not just the last token. So yeah, please make sure you're using the correct code from chapter 5. And then what we can do is we can simply import our utility functions here. So I'm importing the calc loss loader because before we started training, I wanted to just briefly double check what the loss is before we started training. So here I'm just iterating over 5 example batches to calculate the loss to start with. And ideally, yeah, we want to improve the loss as always. And I should also say, for the runtime. So this will be a bit slower than in any of the previous chapters because it's a bit more expensive. We have also a larger model now. We have the 355 million parameter model. And I did run some experiments just to show you, but yeah, just to complete the thought here, we have a loss of about 3.8 and we want to get that down to 0 basically, or close to 0. So here, just showing you some numbers I got when I was running this. So I was running this with a small model. It took about 5 minutes. With this 355 million model, it took about 15 minutes. And this is on an M3 MacBook Air. So I'm running this right now on a M1 MacBook Air. So as you can tell, I like MacBook Airs. It's actually my favorite computer because they are relatively cheap and light and portable. I would say at home, if you don't travel, it's probably overkill to get a separate MacBook Air, but yeah, I like these computers because they are so light and versatile and fast and everything. So in any case, I was running this for 2 epochs and it took about 15 minutes on this model. And so if I'm running this example here, it will probably be taking 20-25 minutes because it's a lower computer and I'm running all that recording setup here and everything. But just to give you the reference numbers and expectations, if you're running this on an A100 GPU, it just takes 1 minute. So it's actually super fast and super cool. You can optionally also run it on the MacBook GPU, like the MPS. Then it's going to be faster than on the CPU, but the results might look slightly different. Also a bit depending on which PyTorch version. When I started working on this book, the newest version was PyTorch 2.0 or 2.1, where I got really much different results. And then every time there was a new PyTorch version, I tested this. And right now in 2.6, the results are very close between CPU and GPU on the MacBook, but still not exactly the same. So I'm running this on a CPU here. But yeah, if you're interested, you can see these numbers and these expectations. If you want to run it on a GPU, for example, using Google Colab or something like that, it's going to be much faster than me here, what I'm doing. But so yeah, let me execute this, run this, and I will probably just edit this video. I usually don't like editing videos because it's a lot of overhead, and so I will maybe make an exception where I will train this, walk away, make myself a tea, and come back. And so, but before I start the training here, I wanted to show you what I'm doing. So I'm again timing it optionally, similar to what I've done in chapter 6. We are using again Adam W, different learning rate. So I was tweaking the learning rate a bit. This was a good one. 2 epochs, you can do more, but then at some point the model will also overfit. 2 was better than 1, and based on what I observed. Again, similar to chapter 5, we will be printing out some sample that the model generates to just make sure, or to track if the model is making progress during training. And that's essentially it. So it's essentially the same training function we used in chapter 5. Nothing too interesting. So I will run this. And before I walk away and make myself a tea, maybe I can also go over some of the bonus materials. So if you go to my GitHub repository, RASBT LLMs from scratch, I do have some bonus material for each chapter. It's like material that is optional but might be interesting. And so I have some utilities here for how I created the data set for this chapter. So I made a few examples, and then I found near duplicates, removed them. It's not something you have to use by any means, but it's just, something I find useful, and so I just shared it here. Then there are some additional evaluation utilities. I would say let's not talk about them now because we will be getting into the evaluation later on, but just so you know, there's an API as a way to use the OpenAI API to evaluate the model, and we will be using a tool called Olama. Also a fun bonus material to generate an instruction data set using Llama. So this is using a Llama model, Llama 3, to generate instruction data. So there are some instructions for doing that if you're interested. What else? Then utilities on improving the data set for instruction fine-tuning. And here, one point where we generate a preference data set. So what is a preference data? So right now, we are tuning the model on instruction data. So instruction data is what we have seen before in this format, but users might have a different preference. Let me see if I have a nicer figure in this one. So I should say instruction fine-tuning is always done for any LLM, usually like ChatGPT LLMs, all the LLMs that are available in ChatGPT, for example, or currently also Anthropic Claudes and Google Gemini. Instruction fine-tuning is a very common step that follows the pre-training. But after the instruction fine-tuning, there is another step people often do, and that's called alignment, or sometimes it's also called preference tuning. So there's pre-training, the instruction fine-tuning we are doing, and then there's also often an optional alignment step, and this uses usually RLHF, which stands for reinforcement learning with human feedback, or DPO, which stands for direct preference optimization. So the original first ChatGPT model, which was, I think, GPT 3.5, it was based on a paper called Instruct GPT. And that proposed this whole reinforcement learning with human feedback procedure. And then Llama 2, for example, they used RLHF as well. And then later LLMs used something else called direct preference optimization because it's a bit easier to implement. And so Llama 3 is based on direct preference optimization. And in general, you can think of both of them as alignment methods. And which one is better? I mean, the jury is still out. I do think I had, if I can find it here, I did have a post on that. I would have to search for this right now. But yeah, so I did write about this at one point where here, how good are the latest open elements? And is DPO better than PPO? So PPO stands for a proximal policy optimization, which is a technique used in RLHF. Long story short, also maybe I can also scroll down and I haven't, here, I just saw it. RLHF and its alternatives if you want to learn more. But long story short, these are two methods for aligning an LLM. So it's essentially nudging the LLM to generate preferred responses. So here's an example where you might have a prompt, an input prompt, where it says, what are the key features to look for when purchasing a new laptop? And there could be two types of responses. One could be more technical. So it says here, when purchasing a new laptop, focus on key specifications such as the processor speed, RAM size, storage type. So this would be a valid response that a chatbot might give to a user who asks about what to look for when purchasing a new laptop. However, a different answer could be more, I would say, general, like think about how it fits into your daily life. Choose a lightweight model, like I do with my MacBook Airs. So if you travel frequently and so forth. So there could be different preferences, and I wouldn't say one is more correct than the other. It's just a human preference. And so with alignment, this is one way when you have the LLM generating different responses to get the LLM to generate a more preferred response. And it's a whole process where you have to prepare the data set and so forth for our LHF or DPO. And here I have a notebook that goes through the steps. Oh, here I wish I had known that before I started talking. So here's also the whole RLHF pipeline. So here RLHF is more expensive because you have an additional reward model that you have to train. But maybe that's a story for another time. So you can do this as an optional step. Here in this notebook, in this bonus notebook, I am implementing DPO, which is simpler than RLHF because it doesn't use a separate reward model. If you use a separate reward model, that means you have to have two LLMs in your compute memory, which is more expensive. And often people prefer DPO because it's simpler to implement. Performance might not be quite as good if you have a fixed data set, but you can iterate over more data points faster. So in that sense, you can compensate maybe for the slight lag in performance modeling performance compared to RLHF, and both both remain popular options. And if you are interested, after our instruction fine-tuning here, if you are interested in aligning your LLM, I highly recommend you to check out this additional notebook, which I have here. So chapter 7, preference tuning with DPO, and then this notebook. And here I'm implementing this from scratch. I did not include this in the book itself because there's also some math involved and it's a bit trickier, I would say. And it's a long notebook and it's very technical. So I thought, okay, this is maybe nice bonus material because it's not, I would say, essential. So the model we are training in chapter 7, it will already be sufficient for answering responses. This is more if you have two types of responses to kind of refine the LLM. So let me see if I have an example of the data. So that for each data point, so we are essentially including a rejected response and a preferred chosen response. Could also be called preferred response. And the chosen response is usually the same as the output, and then the rejected one could be slightly different. So this is what we had in chapter 7, and then I was using the output as here in this case as the chosen one, and then I added a different one, and you can see this one is slightly less friendly. So if a model responds the correct spelling is obviously occasion, it might be a bit, I wouldn't say offensive, but it sounds a bit weird if it kind of like almost like scolding the user or something like that. And so a preferred response might just be like this one. And in fact, this preference tuning is also often used to prevent the LLM from doing sensitive things, giving people instructions to build a bomb or something like that. So in that case, the LLM would recognize this and say something like, sorry, I can't help you with this request. So making the LLM a bit safer in that sense. But also people use preference tuning to reduce the usage of swear words and cursing and these types of things. So, and as you know, there are different types of LLMs out there. There is ChatGPT, Anthropic, Claude models, and then there's Google's Gemini, X's Grok, and so forth. And I've not really used it myself, but Grok, for example, is known to be a bit more offensive compared to ChatGPT. And so this is some behavior you can achieve with preference tuning if you give preferred and rejected responses, and then train the model. So here, if you're interested, bonus material, it's relatively similar Then we have to set up our data set and so forth. It's just a bit more code because it's a longer procedure. And then we fine tune the model. So it's, if you're interested, quite interesting. And then the model will generate responses with a certain preference, essentially. Okay, so this is one of the bonus materials. Let's see how far we are. I mentioned I wanted to make myself a tea. Maybe I don't have to because the model is almost finished fine-tuning here. What else do we have? Let's see. If I go to chapter 7, of course, the exercise solutions, I will not go over those. These are really meant for you if you read the book and want to do the exercises. One more thing here I wanted to mention is the interface. So this is similar to what I already showed you in chapter 6. So here we have an interface based on Chainlit where you can interact with the model similar to ChatGPT. So you can write the query here and it will give you the response. So what I'm saying, similar to ChatGPT here, that means that it looks like that in terms of the interface, the user interface. So this looks quite similar to this one. Okay, so another bonus material, let's just check out the code. So how it works is similar to what we are doing is we are loading the LLM here. And this will be based on the LLM that we have fine-tuned. So I will show you later how we save the LLM and then we can use the loading function. It's similar to chapter 6 actually. And then here, when we extract the response, that one trick I showed you where you just truncate and then replace the response tag so that when you look at the response, I closed it now, but that it doesn't show you all these alpaca formatting styles. And this is also another nice optional material if you want to build a nice little chatbot. Okay, I see it's trained for one epoch. I will probably take a break here, edit the video if I don't forget, and be back with my tea then. Yeah, so I was able to make myself some tea and even finish it because the training took much longer than expected. So in this case, it was about 29 minutes, almost half an hour. And that is just due to the fact that this is a 2020 MacBook Air, pretty old computer, running all the recording software and so forth. But yeah, in reality, also 30 minutes, I'm a bit impatient because I'm recording here, but in the grand scheme of things, this is actually not too bad because people train LLMs usually for weeks or months even. And so here, getting results in half an hour is actually quite cool. It's of course a very simple model, a very simple data set. And so let's take a look at what we got. So we see that the training loss goes down, which is nice. The validation loss goes down as well. It's also nice. And we can see based on our intermediate output that we print during the training that the model is doing an okay job. So we have the instruction convert the active sentence to passive. And so the active sentence, the input sentence is the chef cooks the meal every day. And the model response is the meal is prepared every day by the chef. So I would say this is a correct answer. So this is now the sentence converted from active into passive voice. And so with that, we do have the model generate good text. We also have this end of text token. So we can use that to stop generating text when we use our generate function. Because otherwise, models tend to just keep on generating text. I was training it for 2 epochs. You can see the training loss still goes down. The validation loss, it goes also still down a little bit. But I think this is kind of like reaching overfitting territory. So to see this more easily, I also just reused the plot losses function from chapter 5. And here we can see the loss goes down in both cases. And then the training loss, the training loss here is lower than the validation loss. There's quite the gap. So there's a bit of overfitting. It's not too bad. But so we can see model trains well. The next challenge is really to find out how well, because the loss is only one way of judging it. But what's more important is also to make sure the model generates appropriate text. So one way is looking at these here, but this is just one example and another example. We want to see how well does it actually do on new data, for example, the test set. So the next sections will be concerned with that. So the next sections we will be getting the model ready for model evaluation. So now we have this fine-tuned LLM, and the next challenge will be evaluating numerically how well the model is doing. Because if we have a numeric, let's say, value that we can attach to this model, this will allow us to make progress, right? So if I change hyperparameters here and try different things, try a different model, try a different prompt template, different data set, how do I know that the model is actually getting better compared to this model? So one way would be just as a human looking at these responses, but that would be pretty challenging to do this for a lot of examples and keeping in my head, oh, I feel like this one is better than this other one, and so forth. So we want a more systematic way of evaluating the model. And for that, we need ideally like a score or a number. And so that is what we are going to do in the remaining sections here. So we checked off the dataset preparation, the fine tuning. Now the last stage is evaluating the model. This comes in 3 steps. This first step, this section will be just concerned with extracting the responses and saving them, so that in the next section I can show you a way to evaluate the responses that we have saved. So the code for that is relatively simple. We are going to just use our generate function to generate new text. So the text that the model receives is the input text for each test sample. So here, just for simplicity, I'm iterating over 3 test samples. So let me test data. It's data that the model has not seen before. And so we are formatting it similar to before. We use the model to generate the response. And the response text is then also cleaned similar to before. So we are stripping out the input so that the response doesn't include the input that was already there. So we're stripping out this one. And then we also remove the response tags so that it looks like nicely formatted text. And so let's just see how that looks like. So here we are looking at the first response, and the instruction is rewriting the sentence using a simile. And here the input is the car is very fast, and one potential response, the one that is provided in the test set, is the car is as fast as lightning. And the model response is the car is as fast as a bullet. So I would consider this to be a good response. So I would say here the model, it didn't exactly write is lightning, but I feel like this is a similarly good response. So this would be valid in my view. Looking at the second example, the instruction is what type of cloud is typically associated with thunderstorms. The correct response is, I don't know how to pronounce it, but maybe cumulonimbus. And then the model response is cumulus cloud. So here, I'm not an expert in clouds, but I think the model made a mistake. So here the model generated essentially this answer, where I think this is the correct one. So, however, I would say the model is still, it's generating something. So it's not just gobbledygook. So if we go back to an earlier stage here where we had the model, it was just generating part of the input. It didn't make sense at all. That was the pre-trained model. So I feel like our fine-tuning did something useful. So the model is at least responding in a human readable way, but the answer is not necessarily correct in this case. And the last and third one here is, the instruction is name the author of Pride and Prejudice, and the correct answer is Jane Austen. And the model writes the author of Pride and Prejudice is Jane Austen. So I think this is, I would say this is a correct answer. It's just a bit more verbose. So the model uses more words or more tokens, and this is fine. This is, to me, a correct answer. But you can see the challenge now. How do we evaluate that, right? So here, how do we check that this is correct? Because you can see there's a slight difference, right? You have this versus this. Maybe you can write an automated way of doing this, writing some code, but then how do you deal with cases like this where you have a different word and in this case it's not correct, right? And so this will be the challenge of the next section. I will show you a way of automatically evaluating it. The gold standard, of course, is to have a human expert going through these and then figuring out whether these are correct, but that would be a lot of work if we have hundreds or thousands of test samples. So for this section though, for the remainder, I will just save these responses here so that we can reuse them later in the next section. So for that, what I'm doing is I'm using the TQDM progress bar library. And here in the progress bar library, what I'm doing is I'm iterating over it, setting the length to the size of the test set. So this will make a bar that is as long as the test set. I think it's 110 examples. And then here, this is exactly the same code I have above here, where I'm just using the format, the generate, and then the preparation. And the one new thing that I'm adding here is that I'm assigning this response to the dataset instruction so that we can save it to the JSON dictionary. So let me execute this, and I can talk a bit more about this because this might take a few minutes. So here, what it is doing is essentially generating all the responses for the whole data set and then just saving them. So if I go up again, maybe to the top of this notebook, when we looked at the data set, it had only 3 fields: instruction, input, and output. And now we are adding this field model response for each of these entries, and then I'm saving this. The reason why I'm doing this is because in the next section, I will show you a tool that I recommend. I mean, you don't have to, but you can run it outside this notebook. You can, for example, even run it on a different computer, but for that you would need the dictionary, right? You need to model responses. One way could be, of course, generating them on the fly, but it's not a bad idea just to, since we have the model here in memory, we have trained the model, it's sitting in our Python session actively, so we can just use that model since we have it and generate all the responses, and then we can shut down the model. We don't need it anymore. And yeah, I'm seeing that's also why I like TQDM as a progress bar library. It's estimating it takes about 8 more minutes, 7, 8 more minutes. So maybe I will just make myself another tea or sparkling water, and we'll be back in a few minutes then. So the model has finished processing our test dataset. So let's take a look at one of those and see how it now looks like. So similar to before, we have the entries instruction, input, and output. And then we have also now the model response. So we have that now for the whole test dataset, which consists of 110 examples here. One more thing before we move on, since the training and everything is quite expensive, before, let's say, we evaluate the model in a new session and, things might happen, things might crash or something like that. It's never a bad idea to also save the model. So here, this is just some boilerplate to save the model with the respective name. In this case, if we experiment with a 124 million and 355 million version, this will use the model size as the name dash SFT for supervised instruction fine-tuning. So I should say this is also jargon. SFT stands for supervised fine-tuning. And it's just like a different word for instruction fine-tuning in this context. So some papers, books, they just say SFT, which means doing what we have just done here in this notebook. And so then we are saving it as the model dict like we did in chapters 5 and 6. And if we want to load the model in a new session, we can do it like as follows. So the name here will be GPT-2 medium 355 so and so. So let's just see that it works. So here we can go to our browser and we can see, this has been saved now. It's 1.6 gigabytes. And then, I had this one bonus material that I showed you, this user interface, where you could technically now use this model to build an interface like that if you're curious. So the code is here, and this is loading that model somewhere here. Let me see, load, here. So we are loading that model here if you're curious. Okay, and so with that, we have the model, we have the responses, and then in the next section, I will show you how we evaluate that model. Yeah, somehow we have done it. We are now in the final section. And the final section is concerned with evaluating the fine-tuned LLM that we have just fine-tuned. So here we are in step 9, scoring the responses. In the previous section, we saved the responses. Now we are going to evaluate them systematically with another tool. And so in specific, this will be another LLM. We will be tasking an LLM to take a look at our responses and to give us a score for each of the answers. And this is like one popular way of evaluating LLMs. So there are different ways we can evaluate LLMs, maybe a topic for a future resource on model evaluation. One of them is using another LLM to score the responses. And so for this LLM, we will be using a tool called Olama. So Olama is one of my most favorite open source libraries. It's like one really nice and simple way to run LLMs locally on your computer. So it's an open source library, and even though it's called Olama, which is likely inspired by the Llama models, it also supports other models like DeepSeek R1, Phi 4, Gemma, and many, many others. So they are keeping this model or this code up to date to also always support the latest models. So yeah, and the first step would be, of course, installing Llama. I would suggest going here to the download section. So the website is olama.com, going to download, and then yeah, for your operating system, selecting the respective one. I'm running this on a macOS computer, so I'm downloading this, and it's just wait a few seconds until this is downloaded, and then I'm moving this here to my applications. If you're running this on a different computer, of course, this might work differently. So here we can start it like this. And it will then give us some instructions how to, so we want to install it so that it works on the command line. Click install. I'll type my password for this computer. And then, yeah, we can run the model like shown here. So by default, this will run the Llama 3.2 model. Actually, there are multiple Llama 3.2 models. If I go here, it's like a list of all the models they support. If I scroll down to Llama 3.2, this is the 3 billion model. If I run this command, I mean, of course, I'm just using this because it's suggested, but the first choice, but you can use any of those models. Usually the bigger and the newer the model, the better. For example, these would be, of course, more accurate, the Llama 3.3, the 7B or 405B model, but chances are that you might not be able to run it on your computer. The 3 billion model is actually quite nice. It's a relatively small model that will hopefully work on this computer for sure. So let me make a new terminal here, and then I can enter Olama run Llama 3.2, and this will first download the model. I already had it downloaded on my computer. Once it's downloaded, it will then run it. And so I can then ask questions like, what is your favorite ice cream flavor, for example? And then hopefully this generates a response, and so we can see this model is working. Let's exit this model. So by is exiting this model, and we will use this model in olama.surf mode. So it's cut off in this recording, I think, but if you have in your menu bar this Olama icon, when you run Olama surf, I think this will say something like this. So this means your model is already likely running, in my case, on this Mac computer. Let me quit this in my menu bar. So I'm showing you one way we can run the Olama model in the background, that it is ready. So right now it's essentially running, and then we can use it as the API. It was not necessary to execute it like this if the app was already running on my Mac computer, but it might be different on Linux and Windows. So that's usually how I start Olama. Instead of going here to applications and launching the app, I usually just type Olama surf, and this will make the Olama app available in the background so that we can now query the model with an API interface. So we can see how much RAM is available. I think that's what it means, and so forth. So I'm running this on a very small computer. If you have a bit bigger and better computer, I encourage you also to explore using bigger and better models. And let me also, so I would highly recommend shutting down this kernel here of this current notebook, because you already had this 355 million parameter model in your memory. So this will save some memory. You can then run everything down here, or optionally, you can also make a new notebook. So it's maybe better to keep it more separate. So here, I'm first running some code to just make sure Ollama is running. And, this is just boilerplate code. So it's just printing out whether the Ollama app is running or this surf here is running. So just very simple boilerplate code. And next, so if I'm running this on a new notebook, I'm just loading the JSON file. So this is the file we have just generated in the previous section. So we have this instruction data with our responses. So here we have the instruction, the input, the output, and the model response. That's the modified JSON file. I unfortunately can't make this, I can make it wider like this. So this is this file. And we are just loading it here and into our Python session. And I'm also redefining the format input function. This is the same function we had here, but since I'm using a new notebook, I'm redefining it here. And then it's a lot of code, just copy it here and then explain it. So then I will have some code for querying the Llama model. But by default, so here you can also use Llama 3.2 like the one we used before. So here we provide a prompt. This would be the prompt generated by our format instruction function. We define which model we want to use. So this has to be a model that is available here in Ollama. So when you go here, like I said before, you can find a list of all the types of models you might be interested in. So here, this would be Llama 3.2, the 3 billion model. If you want to use the 1 billion model, you have to append :1b. And then these are just some settings. So we have the model, and this is like an API interface to Ollama now. So we have the model, we have the messages field where we provide the prompt as input, and then we set a random seed, the temperature for the sampling to reduce the randomness, and then the context size. So here we use 2048. We prepare the payload for this API. And then we create a request here. And then we add this header. So this is all very boilerplate code. This is something I got from the Ollama documentation. So if you are curious where this is coming from, this is basically how you interact with the Ollama app with an API interface. I think it's kind of almost like similar to using the ChatGPT API, if you are familiar with that. So I have my response data. I add my message and content and return the response data. So here, this is essentially what the model would respond to us. So what you're seeing here, this one, if we use our 3.2 model, and what did we ask it before? We said, what is your favorite ice cream flavor? So all I'm doing here is I'm interacting with a model in this Jupyter notebook instead of the command line. The reason why I'm doing this is, so if I have it set up like this, I can ask it to evaluate my responses, right? So here now I have this interface instead of using it on the command line in Python, so I can iterate over my JSON contents, my test data, and ask it to evaluate. So how do we do that? And so I have prepared a prompt here. And so I just did some trial and error, and you might want to improve this prompt. But so what it does, it's like given the input, and so this would be the formatted input entry, and the correct output. So this would be the response field. I'm saying, or I'm asking the Llama 3.2 model, score the model response. So the response that our model generated. So if we go here and we look at one of the results, we have the output, right? And then the model response. So on a scale from 0 to 100, where 100 is the best score, score my response or my model response. So let's see how it performs on 3 examples and see if this is roughly doing something useful. So it might take a few seconds. And by the way, this is just a very simple and short prompt. A user actually recommended, who tried a lot of different prompts, recommended a better prompt. So I will have it here and we'll share it with you in a few moments. But let's look at some of the results. So we can see for the dataset response, the car is as fast as lightning. The car is as fast as a bullet. This score is 100 because it is essentially a correct response to say this. So what is it saying? The model response, the car is close but not perfect, and so and so. But it's still giving it a pretty good score of 100. Here, this one is only a 20 because the answer is wrong. And in this case, it's giving it a 100 because the model response is Jane Austen is correct, basically. So it's giving it a 100 out of 100. So yeah, this is one way, instead of us humans looking at all these inputs and outputs or the model responses and the targets, it's one way to get some number out of it. So now the problem with that is it's not perfect. It really depends on what model you choose here. This 3B model is not very strong. It's a very small model still. So it won't be, 100% accurate. It is relatively simplistic. So don't expect miracles from a small model like that. But I think this is a nice model to just show the idea behind this method. Yeah, little insertion here. I wanted to highlight also one great reader contribution. I just remembered there was one reader who provided a good analysis if you go to the GitHub repository and discussions. So a reader provided good analysis of the quality of the evaluations and also suggested a better prompt template. So I recommend checking out this discussion thread here. So here the reader did really an amazing job checking out different prompts and everything. And then finally provided a better prompt for evaluating the responses. So this includes a rubric that gives the model a bit more structure in the response evaluation. And then also, instead of using a scale from 0 to 100, it's just using a scale from 1 to 5. And this helps a bit with the consistency. But personally, instead of, or in general, in addition to just improving the prompt template, I would say the best bang for the buck is also just to use a better model. So in the Olama repository, we can see there are multiple different models. We were only working with this very small 3 billion parameter model. So as a rule of thumb, the bigger the models, usually the better. They are more capable. They give better evaluations also and better, they have better capabilities to analyze the inputs. Also, as a rule of thumb, newer models also tend to do better. So for example, something like DeepSeek R1. So especially the larger models, if you can run them on your computer. As bonus material, this is also very popular, is to run or use OpenAI to evaluate models. So in fact, there are specific models that have been developed to develop other models. One is Fudge. The other ones, I forgot the names. I think Prometheus is one. But I remember reading the papers, and essentially what they did is they used OpenAI, I forgot which models, I think GPT-4o, and created these scores. And then they fine-tuned another open weight LLM to match those scores. And the goal was essentially replicating GPT-4o behavior. But you could also just directly, for example, directly train, not train, but use GPT-4o. So I do have some bonus material in the chapter 7 folder where you go to model evaluation. And then here I have some instructions on how to use the OpenAI API. And so this, of course, would not be free. This would cost some money because there's a usage cost that comes with it, like I mentioned. But this would be the canonical way how people evaluate models. But back to this one, like I mentioned, check out, if you want to, the different prompt suggestion by the user to get more stable responses here. This is honestly just a very simple approach. using a simple model with a simple prompt just to keep things simple and conceptual. So please don't expect miracles from this small model. But yeah, I wanted to show you how this in theory can be used. So here it's a slightly modified version. So we are generating the model scores using a prompt similar to this one. The modification is that we are now iterating over the whole test set instead of only the 3 responses. And here you may notice that the model generates a whole long response. So I'm adding, what I'm adding is essentially a little addition that says respond with the integer number only. So if I go up again, let me just add this here. So the model will then only give us the integer number. And you can see actually the response has changed, I think, to before the scores have changed. So they're not super stable, right? So it's small model. And also, honestly, sometimes I find that depending on the Ollama version, even though I set a random seed and the temperature to 0, I still sometimes get non-deterministic results. So if I run this again, sometimes I get different results. Now it seems like they fixed it in the recent version. So yeah, so this is stable now. So we can see we get a score here, a lower score here because the answer is incorrect, and then almost a perfect score here. It's not perfect, but it is still useful if we have a good model that can evaluate other models to get a rough ballpark number. And so that when we tune hyperparameters, we can see if it's improving the model or not. So here, what I'm doing is I'm applying this to all the 110 entries. And then I'm computing the average score. So here, this is generating the scores. And then, sorry, I'm just looking at this one. The models contain the error. Okay, so yeah, sometimes the model, even though I have this request, respond with the integer only, sometimes it will still respond in a, oh, I've deleted this. It will still sometimes give us the long response, and then of course it's not a number. So in this case, it will fail when we convert here, could not convert score. It will fail when we try to convert it as an integer. So that is what we are seeing here. Sometimes it's still providing this long response, but I'm hoping that for most cases it will give us a number. And then when we have these numbers, what we can do is we can compute the accuracy or the average score. So this is not like the accuracy as we have seen in chapter 6. In chapter 6, it was purely based on whether the model was creating a correct response or not. Here, it is just summing the scores and dividing by the length of the scores. That's how many numbers we have. And so this will be a number, the average score will be a number between 0 and 100. So yeah, so that is what we are looking at here when we get the results. Like I said before, it is a bit flawed. It's not perfect. It's just a bit more automated than having us reading the answers and us judging the model when we do hyperparameter tune the model. But this is also almost like how the real world works. We have these benchmarks for LLMs. There are different benchmarks, like MMLU is the benchmark that is just a multiple choice question answering, which is not super useful because usually when we have an LLM, we want the LLM to write actual text. And so this is one, I would say, one of the most frequently used ways to evaluate models by using another model or a human team to assign scores. So in this case, we get an average score of 51.6. 96 out of 110 answers could be scored. Some of them, as we see here, so it should be 14 answers. 14 could not be scored, which is a bummer, but that's what it is because it's not a perfect prompt. We get a score. What does the score tell us is that the model is not great, but it is okay. Maybe because we see it does sometimes give good responses. So as an encouragement to the readers, maybe try to use the different prompt here, the one I recommended from this discussion board. This might be something to try out and see if it gives you, stable results. And then more interestingly, also when you fine tune the model, for example, when you go through the exercises to compare the model quality before and after the fine-tuning, see how much better it does after the fine-tuning. And then also, yeah, it would be interesting to try, if you can, some of these larger evaluation models. So there's a lot of stuff that you can still try out. So it's maybe the last section here, but it's not the end of, LLM fine-tuning. There are many more interesting things. One other interesting thing I mentioned was in the bonus material, the DPO notebook here, the direct preference optimization, which will additionally choose preferred answers. And yeah, with that, I hope you found these videos useful. I hope they were a bit illustrating how LLMs work under the hood, how techniques work. Again, I must highlight that this is only a very small LLM. It's very limited. It's in a sense, like I mentioned before, when we are curious about how cars work, we are not building a Ferrari, we are building an older, simpler car to understand how the motor works, because for these new Ferraris, you need a whole team, millions of dollars. In the same sense, not real LLMs, this is a real LLM, but bigger LLMs like ChatGPT cost millions of dollars to train, so we are not doing it here. But I still hope this gave you a glimpse into the world of LLMs, and I hope, you do interesting, cool work with LLMs in the future. Maybe if you have a cool project, post it on the forum. There's also this discussion board here where readers post interesting, cool project ideas in the show and tell section. So you have also like some cool reader projects. People worked a lot on low resource languages, for example. There's a lot of stuff you can do with small LLMs that is interesting. And so with that, have fun and happy tinkering.